All right, students, let me try a video solution. I was asked about number 4. And I hope I got this across in the lecture. I think one of the challenging parts of this is the geometry. And this one's not so bad as some of the other concave, convex stuff. But watch, let's just run through the geometry here. And the geometry will all be based upon the law of reflection. This says George's eyes are located 60 centimeters from the floor. So if I were to maybe draw a stick figure here and put the floor, and so here's George's eyes, maybe I'll put 60, I think I said centimeters, but 60 inches. So 60 inches from the floor. His belt buckle is 36 inches from the floor. Okay, so it's got a belt buckle maybe right about there. And I'll put this at 36. Okay. Determine the maximum distance from the floor that the bottom of a plane mirror can be placed, such that George can see the belt buckle image in the mirror. So I'm just going to make a big wall here for a moment and say, all right, so there's a mirror here, but here's the idea. It's the law of reflection. So the light leaving the belt buckle goes in all directions. And the light that goes down here, if the mirror went this far down, would bounce off and hit the floor. Kind of useless for my eyes. The ones that are useful to my eyes are the ones that are important. You see, this one up here would be kind of useless to my eyes, too. It'd go up and hit the mirror if it went that high, and then bounced off and go somewhere up there. But it's the law of reflection that's going to be my clue here. And so if I draw a horizontal line at eye level and a horizontal line at the belt buckle level, knowing the law of reflection, so the light coming in has to equal, or the angle coming in has to equal the angle coming out, and knowing about the eyes are roughly on a vertical line about the same as the belt buckle, I would say that the ray or rays that are important are the ones that's going to come up from the belt buckle, hit the mirror right about here, bounce off in such a way that the angle of incidence equals the angle of reflection, and then goes to George's eyes. So if I were just to draw maybe George's head and George's eyes and George's belt buckle, you can expand this out in detail. Let's see, about 1, 2, 3 lines up. So the light would have to hit about here and bounce off. And if you make a triangle, well, maybe I'll make it right here, triangle. And maybe I'll make a green triangle here and a blue triangle here. It's this angle, which is the reflected angle, and this angle, which is the incident angle. They have to be equal. They share this length here. They have a right angle. So they have an angle, side angle. These two are congruent. Congruent means they have all the distances equal, so that has to equal that. And so we know then from the math up here that the distance between the eye and the belt buckle would be when you subtract these two. So that whole distance is 24. And they'd have to be equal, so that would be 12 and 12. So we would have to hit the mirror about 12 up from the belt buckle. The belt buckle was already 36, so we're looking at 48 inches. So as long as there's a part of the mirror right here, 48 inches above the floor, the light would hit and bounce off. And so if this is a mirror, the bottom of it needs to be at least 48 inches above the floor for you to see your belt buckle. And perfect. And that's all there is to that one. Little geometry. But all these have to do with geometry. Some are a little bit easier and harder. These are congruent triangles. But it looks like the next couple questions I have are more about the concave and the convex mirror, and those are similar triangles. We'll talk about those next.